Okay, good morning to all the participants to this morning session of today. Today we will discuss pipe flows. The pipe flows means we will discuss the application of viscous flow through pipes. By this time you have already gone through the exact solutions of Navier-Stokes equations, and for a fully developed incompressible laminar flow through a pipe, that means through a duct of uniform circular cross sectional area, has already been solved analytically as an exact solution of Navier-Stokes equations. Turbulent flow solutions to flow through pipes are available today, and this can be made, but the advanced theories of turbulence requires the closer models which at some point of time based on empirical informations. So, therefore, what happens in practice, since the flows are all turbulent flows, the range of flow rate is such, as you know, when Reynolds number is more than 2000 in case of a pipe flow, the flow becomes turbulent. So, in turbulent flows always it is not possible to solve the problems via theory or by the theory, or even if theories are developed, they have to be validated by experiments. So, what happens in practice is that the practical engineers, what they do, they use some routine methods to make a solutions to pipe flow problems. Solution means, I tell you by example, that if there is a network of pipes, pipe network system, the engineer wants to know that if you have to provide certain rate of flow through the pipe network, what should be the power requirement, and this power requirement depends upon the pressure drop or the drop in the total energy of the fluid, which is manifested in terms of the drop in static pressure. So, what is the total pressure drop in the pipe network? Even if it is a simple long pipe, then what is the pressure drop in the pipe to force a certain flow rate through this? And if we know the pressure drop and we know the value of the flow rate, we can find out the power requirement. So, in practice, to solve this type of problem in pipes and pipe network, a routine method is used which is purely based on the theoretical foundations. And how this is provided, this routine method, through some well documented information based on experiments and theory. That means empirical and theoretical informations together are well documented and provided either in the form of chart or in the form of figure, which the persons in practice use to solve this type of problem. This is exactly the bridge up between the academy and the practical engineers, the engineers in practice. So, this will be discussed today in relation to pipe flow problems, that is the application of viscous flow through pipes. So, to do this, let us just brush up certain theoretical things and do like this. If we consider, just to start from here, if we consider a fully developed flow through a closed conduit, let us consider a fully developed flow through a closed conduit. The flow takes place in this direction. Fully developed flow through a closed conduit. This is the conduit. This may be two flat plates, this may be a circular pipe. If we take a fluid element like this, a fluid element like this, a fluid element like this, then what are the forces acting on this fluid element? Let us identify. One is the shear stress at the wall, which is acted on the fluid element in this direction, opposite to the direction of the flow, the shear stress tau W. And you consider this length in the direction of the flow of this fluid element is delta x, and the pressure and average pressure over this section is P, and you know that in a fully developed flow already you have seen in laminar flow, the pressure is uniform across a section, either it is an uniform pressure sorry or it is a average pressure at a section. And after a length delta x, let us consider the pressure is reduced. Here we consider a duct of uniform cross sectional area. Now, the frictional force or the shear stress at the wall, what does it do? It decreases the static pressure in the direction of the flow. And let us consider that decrease is given by P minus delta P. Simple approach. If A is the cross sectional area and if we consider P as the weighted perimeter in the flow, it is a two dimensional flow, it is representative picture in two dimension, weighted perimeter P, then we can make a force balance and we can write that the shear stress times the perimeter delta, this is the surface area over which the shear stress is acting, and this equals to P into A in this direction minus delta P into A. So, therefore, if you write this, this P is small p is pressure and big P is the perimeter. Then we get tau W equal to A by P, P perimeter, delta P by delta X. Now, here we are interested only in the values, the scalar quantity, that means we are taking the magnitude of the shear stress, we are taking the magnitude, and here we have considered that delta P is the drop in pressure, that is its magnitude. So, therefore, we represent by an absolute sign like this, it will help afterwards, you see. Now, if we take a limit delta x tends to 0, it becomes A by P, this becomes dP dx. If you take the limit, that is limit, sorry, first I write delta P delta x as delta x tends to 0, then if you write here tau W equals to the scalar magnitude, that the magnitude of tau W, area by perimeter times dP dx, and this formula you have already derived the relationship between wall shear stress and the pressure gradient. Now, if a hydraulic diameter is defined for any closed conduit as 4 times the cross sectional area divided by the perimeter, then it can be written that tau W is equal to this A by P is then hydraulic diameter by 4 times dP dx. Now, in case of a pipe, this hydraulic diameter is D, this hydraulic diameter is D. So, tau W is D by 4 dP dx, already you have developed this equation, and this is very important equation, that shear stress is related to pressure gradient. Physically, what does it mean? It is the wall shear stress that is responsible for the decrease in the static pressure of the fluid in case of its flow through a closed conduit, where the flow is purely driven by the pressure, that is known as pressure driven flow. Now, why we have derived the equation or written the equation in terms of the scalar magnitude, now it will be clear. Now, it is very important information before you is that we define in fluid mechanics a coefficient CF known as skin friction coefficient, which is defined at a point, skin friction coefficient, which is defined at a point, skin friction coefficient CF. In fluid flow, we define always skin friction coefficient at a point, skin friction coefficient by this. This is a very important formula. Shear stress at the wall, the magnitude. I am not bothered about the direction, this is a scalar quantity, coefficient, divided by half of rho into v square, where v is some reference velocity, v is some reference velocity. This is the basic definition of a skin friction coefficient, either for external flows or for internal flows. Now, wall shear stress is the shear stress at the wall which is defined at a point. So, local velocity is the reference velocity is v, sorry, this is the skin friction coefficient. Now, conventionally for an internal flow, this reference velocity is the mean flow velocity or average velocity based on the volumetric flow rate. For internal flow, I am not writing it again, this reference velocity is the flow average flow velocity, which is based on the volumetric flow rate, whose definition is that volume flow rate divided by the cross sectional area. And for external flows, this velocity is defined or taken to be the free stream velocity. So, therefore, this definition of skin friction coefficient is there for both external and internal flows. And for external flows, sometimes the skin friction coefficient is sometimes told or sometimes defined specified as drag coefficient, since this shear stress ultimately exerts a drag force on the surface. This is also true for internal flow, but internal flow usually we use the term skin friction coefficient, and for external flow both skin friction coefficient or sometimes drag coefficient, whose basic definition is this. Now, if I write the expression of shear stress as we have developed in terms of the hydraulic diameter dH by 4 and in terms of the pressure gradient dP dx, then it becomes is equal to this is tau w, sorry, then Cf becomes equal to this divided by half rho v square. Clear? Because tau w I am writing like this. Now, this dP dx in case of a fully developed flow, for example, here in a length, we know that fully developed flow dP dx is constant. That means, pressure varies linearly in the direction of flow, for which the tau w shear stress is constant. So, therefore, this always be expressed as pressure difference over any finite length, because dP dx can be expressed as the pressure difference, because this is always constant, that is pressure drop per unit length is always constant. That is why yesterday in the problem of dimensional analysis we always told that pressure drop per unit length is a function of such velocity, diameter, density. Why? This is because for a fully developed flow delta P by L is constant. So, we are interested with pressure drop over a given length. So, therefore, if this is being just changed in terms of this dH by 4 delta P by L into 1 by half rho v square. This is the definition of the skin friction coefficient Cf. So, delta P by L dH by 4 half rho v square. So, this is basically the skin friction coefficient. So, skin friction coefficient therefore is defined in terms of delta P. Now, what is the job? Job is that in academia we find out the wall shear stress, from which we find out the value of dP dx or delta P by L and find out the value of the coefficient of friction, and this coefficient of friction is ultimately provided in terms of a chart or figure, and then this is being used in practice. So, now with this definition of coefficient of friction, one can write for the use of the practical problems, that delta P over a length then becomes equal to this friction coefficient Cf, which is like this Cf into 4 into Cf into L by dH, okay, delta P into half rho v square, L by dH half rho v square. So, this dH is now represented by d. In case of a circular pipe, the hydraulic diameter is d, 4th cross sectional area into divided by the perimeter. So, this is the dynamic head, this is known as dynamic head. Now, this is therefore used largely by the people in practice, that if I am given the value of Cf calculated by anybody else from theory or experiments, then I can find out delta P for a length L, provided I know the average flow velocity, because here the velocity is the average flow velocity, that is the convention for the definition of this Cf, as I have already told. And if I know the average flow velocity from volumetric flow rate, average flow velocity is flow rate divided by the cross section, I can find out delta P. And this Cf is known as Fanning's by the name of the Fanning's friction factor. This CF is known as the Fanning friction factor. Another person, Darcy, who defines a friction factor which is 4 times the Fanning's friction factor. So that this 4 business is not there. That means 4 CF together is defined as a friction factor which is known as Darcy's friction factor. So, until and unless it is told whether it is Darcy's friction factor given or it is the Fanning's friction factor which is given, we cannot use the equation, otherwise there will be a difference in the multiplication of 4. If it is Darcy's friction factor 4 CF, then delta P is simply the friction factor multiplied by this, which gives the pressure drop over a length L for a diameter D. And if CF is the Fanning friction factor given, then it is 4 CF. Okay. Now, already we have solved the laminar flow equations, that fully developed laminar flow, incompressible laminar flow through a cylindrical tube, that means through a pipe, which is known as Hagen-Poiseuille flow. We have already solved this in Hagen-Poiseuille flow. For Hagen-Poiseuille flow, we have already found from the exact solution of Navier-Stokes equation that F is equal to 64 by Re, or the Fanning's friction factor is 16 by Re. This has already been solved by Professor Suman Chakraborty. So, therefore, we see that for a laminar incompressible fully developed flow, the solution is available by the analytical solutions, that is exact solutions of Navier-Stokes equation. Turbulent flow also we can develop the similar relationship with the help of turbulence models. But what happened is that sometimes a particular, it is difficult to have an unique expression even from theory in case of turbulent models, because it varies from turbulent type of turbulent flow and the extent or the level of turbulent flow. So, usually the turbulent, in situation of turbulent flow, we depend on mostly empirical equations, and even if it is being provided by the theories of turbulent flow, some empirical information is required regarding the wall functions or regarding some empirical constants used in the turbulence models. So, therefore, it is better to base on the empirical information, since the theory also are being calibrated by the empirical information or the experimental results. With this in background, though earlier days the turbulence models were not known, what was done was like person first started is known as Stanton, who made series of experiments to find out a relationship between delta P, that pressure drop, and the flow rate, okay, for various pipes of various diameters, various materials, various liquids, and he wanted to make a documentation of results to show the variation of pressure drop with Q for different fluid, different diameter, which I told you earlier in that earlier class, that this as a function of diameter D, the length is taken here, the viscosity, the rho, and the average velocity or the Q. So, this relationship, to explore this relationship, we started a number of experiments, which was followed by another German scientist who is a very reputed scientist, Nico Ratze, who also did a series of experiments on pipe flow to develop this relationship, the dependence of pressure drop per unit length or pressure drop over a given length as a function of all these parameters. Then ultimately all this information given by Stanton and Nico Ratze were comprehensively documented by the person known as L. A. Moody in terms of the friction factor, as I have defined you, Darcy's friction factor, as a function of Reynolds number. From dimension analysis also it is found that friction factor is a function of Reynolds number only. From theoretical analysis also, in a laminar fully developed incompressible flow, we have seen that if we define the friction factor this way, then friction factor becomes a function of Reynolds number only. Theory also proves that. So, therefore, friction factor is a function of Reynolds number. So, in terms of two parameters, one is the dependent parameter and as an independent parameter, Moody made a comprehensive documentation of all the results of the pipe flow for different pipes of different diameters, different materials, different liquid, and finally he plotted in terms of figure. Now, before that I tell you some of the expressions just for your information. You do not have to remember, do not think that F is equal to Darcy's friction factor 64 by Re, it is laminar flow, laminar fully developed incompressible flow, laminar fully developed incompressible flow. Then I told you that a single formula or unique formula does not work in turbulent flow. Turbulent flow, one important formula which sometimes used empirical 3164, this is for your information I am telling, Re to the power 1/4 divided by Re. This is due to Blasius. It is scientist Blasius, we tell it is, these are very important equation, Blasius equation, and it is valid in the turbulent flow so long Reynolds number is less than equal to 10 to the power 5. Above 10 to the power 5, mostly covering a very high Reynolds number, one very important formula is there, F is equal to minus 0.8 plus log base 10 into Re into root over F, and this is due to Prandtl, famous man who discovered the boundary layer, Prandtl and von Karman and Prandtl. Now, it was found that the pipe roughness, all commercial pipes has roughness. What is the roughness? There are surface protrusion, surface grains, surface irregularities which are protruded from the surface. This affects the pressure drop very much. So, if the surface protrusion or surface roughness, which are heterogeneous in nature, surface roughness varying in their heights. So, however, if the surface roughness is different, that means it influences the pressure drop after a certain flow. That means especially in the turbulent range, it is the surface roughness which matters a lot in the pressure drop. So, it was expected that F is not only a function of Reynolds number, but also it is a function of Reynolds number and the surface roughness, and this is expressed as some mean surface roughness divided by the diameter. This is known as relative surface roughness. This is a non-dimensional parameter because everything is non-dimensional or dimensionless, we expressed in terms of the dimensionless parameter. So, then what happens, scientists or engineers try to develop expression between the friction coefficient and the Reynolds number and the relative surface roughness, that is this average surface roughness divided by the hydraulic diameter or the diameter of the pipe. Now, this average surface roughness is some average of the varying roughness in the commercial pipe. What was made in the experiments, that a pipe was taken, a smooth pipe, and artificially the roughness was created by gluing the sand grains of uniform size which represented the roughness of the commercial pipe, which gives the identical result as far as the flow rate and pressure drop is concerned. And in that case, the uniform size of the sand grain in the commercial, in the pipe in the experiment is used to specify the average roughness of the commercial pipe. This is the way the experiments were made and the average roughness of the commercial pipe was specified, and finally a relationship was developed like that. One such relationship due to Colebrook and White, I am telling you, 1 by root F, which is very popular, 1.74, but do not think that I am writing this is because you have to remember this. This is for your background information, that is epsilon by R plus 18.7 Re root F. I am not also remembering it, I am writing it, seeing that thing, minus, this is minus, you see, I also do not remember it. That means this is a philosophy, that means that researchers developed this type of equations where friction factor, this R is the radius of the tube, depends upon the Reynolds number and also upon the relative roughness. So, now all these empirical informations and the experiment, this is the data from the experiments of all these scientists, Stanton, Nicuretze, well, Carman, Prandtl, were well documented by Moody in terms of a diagram known as Moody's diagram. So, what is this? I show you. This diagram is like that. One side the ordinate is friction factor and this is Reynolds number. So, Fc is Reynolds number, this is friction factor and this is a log-log plot. In laminar flow, the curve is like this. That means up to 2 into 10 to the power 3, this is the linear in log-log curve with a negative slope. This is friction factor is 64 by Re. Now, there is a zone when the transition from laminar to turbulent takes place, there is a discontinuity. This is not defined in this diagram. So, after certain thing, this is a typical critical zone. When the Reynolds number is 2000 and above, the transition takes place to turbulent. Then the graph shows like this. Let me first draw, then I will explain it. I will explain you. This is different epsilon by d. This is given in any book, you may not have to take note, you just see to it, I will explain. This is the increasing value of epsilon. Now, what is this? Now, what happens after this critical zone? This is the empirical information. This graph, this figure is for smooth pipe. This is known as hydraulic smooth pipe. This graph is for smooth pipe. Now, the question comes, what is this smooth pipe? So, here you see the friction factor is inverse function of Reynolds number, similar way as we developed in laminar flow. The definition of a smooth pipe is such that its roughness is so small, all pipes are rough. For example, the compressible, incompressible fluid, all fluids are compressible. When its bulk modulus is so high that even under extremely high pressure, the change in volume or density is insignificant. So, similarly, all pipes are rough. A smooth pipe is a pipe where the roughness is so small that a change in the roughness in that regime does not change the pressure drop flow rate characteristics. The physical explanation I will tell you afterwards. This is known as the smooth curve equation. So, this is the smooth curve equation. No epsilon by d is prescribed for you as if it is 0, as if it is 0, as if it is practically 0. Now, this curve for different epsilon by t have two characteristic features, that all curves for different relative roughness ultimately coincide at low Reynolds number to this smooth pipe. Well, this coincides with this smooth pipe, and it is found that the curve having a higher value of relative roughness branches off from the smooth pipe early, whereas a curve having a lower values of relative roughness branches out from the smooth pipe late. Okay, so, branching off takes place at Reynolds number, late means with respect to Reynolds number, at higher Reynolds number depending on the relative roughness. These are the informations. Another information is that all curves for rough pipes at high turbulent flow, that is higher values of Reynolds number, are parallel to this abscissa, means the friction factor is independent of the Reynolds number. So, these are the informations which are being documented in this figure by Moody, and this diagram is known as Moody's. I will show you the diagram from a book, taken from a book, but you understand here from my this figure. So, this zone is the laminar zone. Obviously, this is an exact solution, already we did it, that F is 64. This zone is defined as critical zone, critical zone. Now, this zone where all these smooth pipes almost coincides, I could not draw it well, almost they converge and coincides with the hydraulically smooth pipe line. this zone is known as smooth zone of flow, smooth zone of flow, smooth zone, smooth zone. And this zone, where if we take this point where this becomes parallel, this point, this zone is the rough zone. This is definition. Rough zone is that zone where the friction factor is independent of Reynolds number, and this zone is known as transition zone, transition from smooth transition zone, transition zone. My handwriting is not good, but I am telling you everything verbally so that you can understand. This is, that means transition from smooth zone to rough zone. Now you can see it by a figure. You see it, you show the figure uploaded. Yes, you see that figure, that this is the figure you see here. This is the laminar flow, this graph is for laminar flow. This is the hydraulically smooth pipe. As I told that the for different relative roughness the curves are different, which is the increasing direction of relative roughness, all converges to the smooth pipe at low Reynolds number, and all curve branches off from the hydraulically smooth curve at different Reynolds number. Lower is the value of epsilon by d, it branches off at a higher Reynolds number. That means in a lower range of Reynolds number it coincides with the smooth curve, and this is the locus of the points from where all these curves become parallel to the abscissa, that means the Reynolds number, that means friction factor is independent of Reynolds number. So this zone is the rough zone, this zone is the transition zones, hydraulically smooth zone and the laminar flow zone. Now I give you an physical explanation that in laminar flow what happens, the protrusion or roughness does not make any change in the flow, because any disturbance created by this protrusion is solidly dampened out by the viscous damping, since the flow is laminar, until and unless these protrusions are large enough to create a very high disturbance, and in that case we consider it as a change in the effective diameter of the pipe. So therefore within certain range these protrusions cannot make any change in the laminar flow. Now hydraulically smooth flow, or we tell that smooth flow pipe, that is the smooth pipe, those pipes where the roughness is so small in the range of very small lengths, that protrusions, they are all submerged within the laminar boundary layer, sorry, the laminar sublayer. In a turbulent flow, as you know, that near the wall, in the vicinity of the wall, there is a laminar sublayer, there is a sublayer, shear layer, sub-shear layer, you can tell, which is laminar in nature. Now when the Reynolds number is low, the value of the laminar sublayer is high. Now if the roughness is very very small, tending to 0 for example, in that equation I showed you that when the Colebrook and White equation, here you see that when epsilon tends to 0, this is 0 theoretically, that friction factor is independent of Reynolds number. You understand, when epsilon, again when Reynolds number tends to infinity, you see, then friction factor ceases to be a function of Reynolds number. This is a very important relation, that is why I told Colebrook White. So friction factor is independent of the Reynolds number, depends only on the surface roughness. So therefore when surface roughness tends to 0, then what happens, under all Reynolds number, laminar thickness of the laminar sublayer is sufficient enough to make those protrusions submerged, and no effect in the main bulk flow to make a change in the relationship between friction factor and Reynolds number. Okay, and this is the reason by which that low Reynolds number, the all curves of different roughness coincides with the smooth flow. This is because at low Reynolds number the laminar sublayer thickness is high compared to the protrusion. So it is the relative magnitudes of the thickness of the laminar sublayer and the roughness of the pipe, or the relative roughness of the pipe, which makes whether the pipe will be totally smooth in all range of Reynolds number faced in the practice, or it will be smooth up to certain range of Reynolds number, then it will be rough. And a completely rough zone where the friction factor is independent of the Reynolds number means that if you see the equation, that delta p there is proportional to the square of the velocity, is almost square of the velocity. If delta P is proportional to the square of the velocity, you see in the definition that friction factor becomes constant. It is not a function of the flow velocity or the Reynolds number. Okay. So, after this, now I tell you that in this connection there are usually 3 types of problems with respect to pipe flow. With respect to pipe flow, usually there are 3 types of problem. One category, now problem is that rho and mu are always given, Now there are 3 types of problem, that what are the parameters? The volume flow rate, okay, the diameter of the pipe, the roughness, epsilon roughness of the pipe, average roughness, and delta P for a given length, or delta P for a given length, that is the pressure drop over a length L. So, length I am telling because pressure drop per length over a length L, and at the same time we can find out the power. If we know delta P and Q, we can find out the power required to provide that flow through the pipe of certain diameter and having a pressure drop delta P. Now, let us find out that 3 types of problem is there. Now, first of all I write that Reynolds number is defined as rho V d by mu, where V is defined as flow rate Q divided by pi d square by 4, rather 4 comes here, pi d square. All the formula I write in front of me. Then delta P is equal to friction factor, which is provided by Moody's diagram. This is extremely simple, over the length L, L by d, then half rho V square. Now, these are extremely simple thing. One case we know Q, first one Q known, T known, epsilon known. We have to find out delta P. This is the most simple. When Q is known, we know the value of Re. I am not solving any problem with numerical value. I tell you directly the value Re is known, because we know the flow rate, we know the average velocity, Re is known. When epsilon is known, epsilon by d is known. So, Re known, epsilon by d known. So, we know the friction factor and we can find out delta P from here. This is a straightforward calculation, explicit method, and we can find out the pressure as the power as Q into delta P, power requirement. This is another important thing. So, this is number 1 problem. Second category of problem is that Q is not given, D is given, epsilon is given, delta P over the length given. Q is not given. When Q is not known a priori, we do not know the Reynolds number a priori, because we do not know the velocity. So, in that case, to proceed, what happens? You cannot proceed directly, straightforward. We have to make an iteration. We have to guess a value of f. Some value of f is guessed. So, when f is guessed, then from this equation we can find out the value of L by d half rho V square. So, the value of Q is not known, the value of D is known, the value of epsilon is known, and the value of pressure drop is known. So, therefore, when Q is not known, if you guess the value of F, from here we can find out the value of V. That means we use this equation, pressure equation, we can, this is known. So, we know the value of V. When V is known, Reynolds number is known, epsilon is already known. So, when Reynolds number is known and epsilon is known, we can read the value from Moody's diagram and can update this guess value. And this way iteration is made until and unless the value of F is converged. So, convergence depends upon the initial guess value. Clear? Now, another option is that Q is known, epsilon is known, delta P is known, D is not known. So, either Q or D is unknown, then this becomes an iterative thing. When D is not known, a priori I do not know the Reynolds number. But since this is known, delta P is known, if I guess F, again guess F, then you can find out V. So, when we guess F, delta P is given, either we can find out V if it is not known, we can find out D if it is not known. Here D is not known, number 3 category. So, guess F and find out D from here. Then you know the Reynolds number. When Reynolds number is known, and epsilon by d is known, then F can be known from the Moody's diagram, compare with the guess value, substitute this, again repeat the process iteratively, you make a solution. That means these two equations you have to remember the definition of Reynolds number, and delta P over a given length is expressed in terms of the friction coefficient like this. So, use of these two will solve you the problem. It may be iterative, it may not be iterative depending upon what are the parameters to be given. And finally, the power requirement is found from the flow rate into the pressure drop. Now, I come to some practical concept that see that if there is a pipeline, now there is a flow. Grossly the concept is like that. When the flow takes place, inlet is 1, outlet is 2 section. So, flow takes place, flow. Why the fluid flows? Because of the energy gradient, we know. Because of the energy gradient, that means total energy at 1 is more than the total energy at 2, and while it flows, the difference in energy is taken care of by the loss in energy. And this is the Bernoulli's equation that tells that total mechanical energy at inlet, if you take along a streamline, then at any point at the upstream and any point at the downstream, the difference of energy equals to the total energy loss along the flow. What is this loss? That has to be emphasized. I think Professor Suman Chakraborty has already emphasized this. Energy is neither lost nor created. So, conservation of energy in its general form, as you will see in thermodynamics or heat transfer, where we write the general conservation of energy, there is no loss term because it takes care of all forms of energy. But when you tell or when you talk about Bernoulli's equation, it is the conservation of mechanical energy. So, we will make the budget of mechanical energy. So, what happens if some form of mechanical energy is converted to any other form of energy that is not coming within the budget of mechanical energy? So, if there is an exchange between one to another only within the framework of mechanical engine and energy, so that is loss. So, that is known as the loss of energy, that is loss of mechanical energy. So, here we take all the mechanical energy, kinetic energy, this is the pressure energy which comes from the concept of flow work and the potential energy. So, therefore, here is the loss term. So, otherwise in conservation of energy, loss should not be there because there is no loss in energy. Energy is neither lost nor created, that it is the conservation of mechanical energy. Now, if we define the energy per unit weight as head, which is a terminology used in hydraulics engineering and for all engineers in practice, hydraulic engineers, and if this is the energy per unit weight as H2, that is the energy, total energy per unit weight, energy per unit weight, and this dimension is equal to the meter. So, if you speak in terms of the energy per unit weight, it can be energy per unit mass. So, this H1 is equal to definitely by the conservation of mechanical energy losses, means this is the mechanical energy which is being converted by the friction of the fluid into intermolecular energy. That conversion we call it as loss, and in our scientific term we call the mechanical energy is dissipated into intermolecular energy, sometimes we call loosely in terms of heat. And this dissipation in case of fluid flow is manifested in terms of a loss in static pressure. Why? Because here the flow velocities are conceived in terms of the volumetric flow rate. Volumetric flow rate by cross sectional area is considered to be the average velocity. Even if this is there is an uniform velocity that must define the flow rate which has to be constant throughout for a steady flow. So, therefore, in case of fluid flow, this curtailment of mechanical energy into intermolecular energy through friction is being realized through a decrease in the static pressure. So, therefore, this is actually this losses is the causing the decrease in the static pressure. So, therefore, we see that the difference between the total head at inlet and outlet should be the losses simply from the, that means losses in head, that means losses in energy per unit weight which is actually being converted into intermolecular energy. So, this is the basic concept that whenever we solve any pipe flow problem, we must see that what is the energy difference at inlet and outlet which causes the flow, this energy gradient, and this must be overcome by the total resistance suffered, that means losses in head. That resistance actually converts this energy into intermolecular energy, which we conceive in terms of the loss. Now, this can be explained in a much better and simpler way like this. Let us consider the flow from one tank to the another tank. Let us consider a case like this, the flow from one tank to the another tank like this, which is simple to understand, and let us consider we make the height of the tank constant at these two levels. So, tank A and let us tank B, and there is a flow. Let us consider a very simple case, consider the height to be same. Now, why the fluid is flowing? Because of the energy. If you consider a point here 1 and you consider a point here 2, then definitely if you justify, if you consider the 2 points, you see the energy content in any fluid element here is higher than here. So, if you connect these 2 points via a fluid path or fluid circuit, the flow will take place until and unless this energy is balanced. But if you maintain a constant height, that means this energy at constant, this energy at constant, then the flow will continually take place. Let us consider from any reference datum, this height is Z1 and this height is Z2. Now, if we simply write the energy equations at these 2 points, or in Bernoulli's equations along a streamline connecting these 2 points, then what you will get? You get the, here the head is energy per unit weight is Z1. Well, there is this Z1, Z1 is the potential energy because the pressure is 0, because if you write everything P1 by rho g plus V1 square by 2g plus Z1 equals to here P2 by 2 rho g. Simple application. We are not going for any differential equation, any complicated assumptions. Simple application. This is valid from the conservation of losses, as I have discussed. Now, since P1 0, because atmospheric pressure 0 or cancelled, if you put the atmospheric pressure, this is cancelled. There is no velocity at this surface, there is no velocity at this. That means it is the difference in this, only this, in this case only the potential difference, the difference in potential energy is equal to the losses. Now, this difference in the potential energy, just like that I discussed earlier, that it is considered to be the total head, total energy per unit weight at inlet, total energy per unit weight at the outlet. Inlet means that this point, extreme this point, not here. So, that means this is equal to H losses. That means this equal to the losses that have to be overcome during the flow. So, this is known as head causing flow or potential, head causing flow, or this is known as flow potential. Flow, it can be seen, flow potential, flow potential, flow potential, or, and this is the loss, this is the head loss, energy loss, flow potential and energy loss, and it is due to the flow resistance. Now, if I write the equation, if I write the equation for the head, that is the loss. Now, can you see this? This is the problem. Okay, can they see this? Okay, can they see this? Now, you see, if I write now, you can see this. Now, if I write now Z1 minus Z2 is the loss, is the head loss. What are the losses? You try to find out. First, when the fluid comes through this, from this big tank to this small pipe, there is a loss of energy, and this loss is known as entry loss, H entry. That means head loss, energy loss per unit weight is entry loss. Then when it flows through this pipe, then there is a frictional loss, skin friction. This is known as frictional loss, or this is loss due to skin friction, which is already I have done FL by D V square by 2G. Now, when the fluid goes out, then there is a loss which is known as the exit loss. Exit loss. This I will come afterwards. First of all, you assume now the entry loss equal to 0.5 times, this is expressed in terms of this is per unit weight, that is why I am writing V square by 2G. The exit loss is expressed in terms of 0.5 V square by 2G. That means there is a loss of mechanical energy manifested in terms of the pressure loss because of this entry, that is entry loss from the big tank to the small pipe, which is given by V square by 2G, where V is the flow, average flow velocity through this pipe. Then friction loss already we have seen, FL by D V square by 2G, FL by D V square 2G. This is the loss of head energy per unit weight by the friction, that means delta P by rho G. Delta P, that is the loss of pressure due to friction, this is known as skin friction loss. Delta P by rho G, if you know that delta P is how? FL by D half rho V square. So, delta P by rho G becomes V square by 2G. This is the loss, that is the energy loss due to, that is the loss in pressure energy due to skin friction, and exit loss is given by V square by 2G. This is probably you can understand from your physical concept, that also I will explain now, that exit loss means what is that? That when it is coming out, it is coming with the velocity V. Now, if we could have written the energy equation or Bernoulli's equation, this taking this 2 at this section, then what happened? I could have written here V2 square by 2G, not 0, because here the fluid has come to rest, but here the fluid is V2 square by 2G. In that case, this exit loss could not have been there. That means that since V2 square by 2G is not written here, this has come in the form of exit loss. Means if you take the Bernoulli's equation here, you get the same expression, but here it will come as the kinetic energy here, because here there is a kinetic energy velocity, but here there is no kinetic energy, it will disappear, but it will come in the form of exit loss, which means that this kinetic energy is ultimately what happens? Being dissipated in the form of eddies and increase the intermolecular energy. That means this entire kinetic energy is being lost, is being degraded or dissipated through intermolecular energy. The fluid comes to rest. A high speed flow comes, and if you arrest it in a big chamber, so fluid comes to rest. If you measure the temperature will increase. That means the entire kinetic energy is, the fluid is brought to rest, the kinetic energy is being converted into intermolecular energy. This is purely by the friction at the molecular level, fluid friction. So, therefore, this kinetic energy is ultimately disappears, means it is lost from the mechanical part of the energy, degraded into intermolecular. That is why when you take the Bernoulli's equation, outlet point is 2, this point, then it appears as the exit loss, otherwise it appears as the velocity or kinetic energy velocity head here. So, if you do that, then now it is clear that this becomes equal to this. Now, if you make this as your thing, that then it becomes, you can write this as 1.5 plus F L by D into V square by 2G. That is Z1 minus Z2. That means this is the delta H, which is the head causing the flow. Now, V can be written as 4Q by pi D square. That means flow rate divided by the cross sectional area. So, V square is 16Q square by pi D4. So, if you substitute this, you will get an expression delta H equals to, if you substitute this V in terms of Q, you get an expression, this is simply arithmetic or algebraic, what is called algebraic rearrangement, F L by D into 1 by pi square D 4 G into Q square. this can be it can be replaced by R. So, if we write this in this form, delta H is R Q square, where R is 8 1.5 plus F L by d pi square d 4g. That means, if d diameter is constant for the pipe for a given length L, it is given by a friction factor F. In case F is constant independent of Reynolds number in high turbulent flow zone, this is almost a parameter of the pipe, which is known as the resistance. If F varies with flow rate or the Reynolds number, then the resistance will vary with the Reynolds number. So, this is a equation which is known as the flow equation. This is similar to all phenomenological equation, that the head causing the flow, that means energy causing the flow, energy per unit weight is head, that the difference between the 2 points in the flow circuit is equal to the resistance times the square of the flow rate. This can be shown by an analogous electrical circuit is like this. An analogous electrical circuit like this, where this is delta H, this is the Q square, and this is same as the DC circuit, and it is just like the Ohm's law. Delta H, only difference is that here the flux is not linear. Delta H, that is the potential, is proportional to the flux resistance into the flux square of the flux. That is the only difference. So, Q square is the flux, and this. So, by analogous electrical circuit we can explain this. Now, after this I will tell you about the losses, expansion and contraction losses, which will tell you the concept of entry and exit loss. So, first you see the losses due to sudden expansion, losses due to sudden expansion. What is this? What is mean by expansion or sudden enlargement in the area? Sudden expansion takes place when the fluid flowing through a pipe gets immediately a sudden enlargement. In many of the practical applications, there is an enlargement in the area takes place. The sudden enlargement in the area, cross sectional area, what happens physically? Let us see. The flow takes place here. Now, flow comes with some uniform velocity, for example. Let this section is 1 and V1 is the velocity. At the outlet, for example, here the fluid goes with a velocity, another velocity V2 out, this is V2. Now, since the area is increased, we know V2 is less than V1 and P2 is greater than P1. That is true. There is no doubt in it. There is no doubt in it. But question is that what is the loss? That means this P2 and P1 is related from Bernoulli's equation by V2 and V1. So, since V2 is decreased, P2 will be increased. So, increase in P2 will take place only by the change in V2 by the Bernoulli's equation if we neglect the losses. Now, what is this sudden expansion loss? But if you consider the frictional loss, then there will be losses. For example, first for your concept I tell you, these are the concepts, deductions are not the concepts, everybody can do it. That for example, I tell you here P1 by rho plus V1 square by 2 is P2 by rho plus V2 square by 2. Now, you see that P2, let us consider the incompressible flow, P2 minus P1 by rho is equal to V2 square minus V. Why? Because no loss, loss is 0. That means, if you consider an ideal fluid, the loss is 0, then P2 should increase the way V2 should decrease. Sorry, P2 should increase the way V2 should increase, because V2 increases from V1, that is why P2 also increases because of the Bernoulli's equation. When V2 is decreases, then P2 increases. So, this will be P2 V1, sorry, V1 square minus V2 square, sorry, V1 square minus V2 square. So, the increase in P2 is manifested by the decrease in V2 by this amount if there is no loss. But if there is loss, says then what will happen? P2 minus P1 by rho is equal to V1 square minus V2 square by 2, then this will not be 0, then P2 minus P1 by rho, this minus losses. Try to understand. That means this decrease in pressure is less than that because of the change in velocity by this amount losses. Now what is this loss? This losses is due to the skin friction, and if we neglect the skin friction, if you make a very short duct, another loss will be added here, which is because of this. Even if we neglect the skin friction, another loss will be there which we cannot neglect, that is due to this sudden expansion. And if it is a long duct, then what happened? This skin friction, that is the frictional loss, plus the losses due to expansion. These losses due to expansion now, only due to expansion now I will derive. So this is the concept actually, that the pressure changes because of the losses only I will find out. So now if we do that, you will see that let this be the section. We take this is at the inlet 1 and this is at the outlet 2. This is V1, this is V2. Now what we will do, what happens that the flow takes place here like this and flow comes out here like this. Again I am drawing this figure. So streamline when comes here, it has sees an increase in cross sectional area, the streamline will divert like this. Now while doing so, what happens, there is a separation at this zone and there is a flow reversal takes place. Fluid flows in the opposite direction and creates eddies. This is known as boundary layer separation. I think Professor Ghosh Mollik has told it that when fluid flows from high energy to low energy, what happens when fluid flows against an adverse pressure gradient? Here what happens? The fluid flows against a high pressure. Here the pressure is high, here the pressure is low. As you know, the velocity is reduced here, so pressure is increased. When fluid flows against an adverse pressure gradient, by virtue of its kinetic energy, then what happens? The fluid particles very close to the wall, which have lost their kinetic energy because of the momentum interaction with the wall, because near the wall fluid particles are slowed down, they cannot surmount the adverse pressure, and therefore they move backward, they move in a reverse direction where they get the favorable pressure forces from higher pressure to lower pressure, they cannot move downstream. This is known as separation. This happens near the wall when the fluid flows against an adverse pressure gradient. Fluid had to surmount the adverse pressure and fluid does it. Many situations flow through a diffuser, we know fluid flows from a lower pressure to higher pressure, but it flows from a higher energy to a lower energy. So energy gradient makes it to flow, that means kinetic energy is counterowing its adverse pressure energy, that adverse pressure gradient. But fluid particles which lose the kinetic energy near the wall because of the boundary layer, because of this momentum interaction with the wall, that means momentum interaction between the fluid and that is with the wall interactions, the fluid comes at rest at the wall. If the wall is at rest, that is the no slip condition. Fluid particles, the kinetic energy of the fluid, velocity of the fluid becomes very small near the wall. They cannot surmount the adverse pressure, so they flow in the opposite direction. This is the boundary layer separation. I will not waste time. So because of this separation, there are flow reversal and eddies formed and the pressure is sufficiently reduced. If this pressure is P2 and this pressure is P1, P2 is greater than P1, then this pressure if we denote by P dash. Now let us take a control volume like this. Let us take a control volume like this and apply our linear momentum conservation equation. Then the net rate of momentum efflux in this direction, direction of flows X, is the momentum out, that is the mass rho A2 V2, that is the mass flow rate, into velocity, minus rho A1 V1 into momentum V1. So rho A2 V2, V2 minus rho A1 V1 V1, it is the momentum, equals to what? The net force acting in this direction. What is that? P1 into this area A1. Let us consider the inlet area A1, outlet area A2, minus plus this is the control volume we are taking, So, this control volume means we have to take this part also. That means if you take this as the control volume, so there is a, that means I take the control volume like this again. Let us take this as the control volume, otherwise you will not understand. So, the pressure is acting on this part of the streamline. That means this is P1 into A1. So, pressure acting on this part is plus P dash into this is A2 minus A1. This cross sectional area is A2 minus A1, projected cross sectional area of this curved surface, okay, minus P2 into A2. Now, by experiment it has been found that P dash is P1. This you have to accept, from experiment it has been found. So, therefore, P dash A1, this is cancelled out. Now, this I write rho A2 V2, rho A1 V1 is rho A2 V2. So, any one will go, V2 minus V1 is equal to this P1 A1 will be cancelled. That means P1, P dash is P1 minus P2, oh sorry, P1 minus P2 into A2, I am sorry. Now, if I write the Bernoulli's equation between these 2 points, that 2 sections, rather P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2 plus the loss of energy per unit weight, loss of heat, which we want to find out. This loss of heat is only because of this. We consider as if there is a loss of heat. Now, if we substitute P1 minus P2 by rho from this expression, that P1 minus P2 by rho is rho A2 V2 V2 minus V1. So, this is rho 2, this A2 you can cancel. Next page. So, from the momentum equation I got P1 minus P2 by rho is equal to V2 into V2 minus V1. Okay, P1 minus P2 by rho is V2 into V2 minus V1. And here we get P2 minus P1 by rho, in any way we write P2 minus P1 by rho is V1 square by 2 minus V2 square by 2. Now, P1 minus P2 minus P1 by rho is minus of this plus the losses. So, if you substitute this here, that is the, with a minus sign, this is P2 minus P1, P1 minus P2. That means, if you substitute, eliminate the pressure drop P1 minus P2 from this equation here, you get H loss is equal to V1 minus V2, that is an algebra whole square. Here I am sorry that I must write in terms of head, that is energy per unit weight. Now, we are dealing with energy per unit weight, head. So, therefore, the loss of energy per unit weight due to sudden expansion is given by V1 minus V2 whole square by 2g. That means, if there is an sudden expansion and I have a velocity here V2 because of the expansion, and here the velocity is V1, V2 is less than V1, then loss is given by this. Now, if I write in terms of V1, then from the average continuity equation over the cross sectional area, this is the velocity. This velocity is considered to be the uniform velocity or the average velocity. We are not going through any distribution and all these things. So, V1 by V2 is A2 by A1, this is by continuity, V1 A1, this is A1, this is A2 is equal to V2 A2. That means, V1 square by 2g, or we write V1 A1, that V2 is A1 by A2, 1 minus A1 by A2 whole square. So, in terms of this also we can write. If you write this way and see that if this A2 is very, very greater than A1, that means A2 tends to be a very big value compared to A1, which represents a case of exit. That means, this go to a big tank from a small pipe. When exit means physically from a small pipe it goes to a big tank. So, A2 is very, very greater than A1 is the case of exit, then this becomes 0. negligible, then the exit loss. Then a special case of the loss due to expansion is an exit loss when this downstream area is much more than the upstream area. That means expansion, the sudden enlargement is very large, and that is physically the case of exit. Okay. So, that is the exit loss. Now, when you talk about the contraction, I have told that now this thing will come, now contraction loss. Contraction loss. Contraction loss. What is contraction loss? Just the reverse. If fluid comes like this, suddenly this is contracted in the direction of flow. Here what happened? There is a section 1 where the fluid is coming with some velocity V1, and here it is going out with some velocity V2, and because of this V2 is higher than V1. Now, what is this loss here? Here what happens? The streamline goes like this, and as you know that in this type of case the streamline ultimately converges, because streamline starts converging before the contraction takes place. This is because of a change in the momentum, a lateral force is acting on it, and that suppresses the streamline to attain a minimum area known as vena contracta. Again streamline expands like this. So, vena contracta, this is probably have been taught vena contracta earlier. Now, what happens when the streamline converges up to vena contracta area, where I consider the cross sectional area of the stream tube is minimum, this is AC, the cross sectional area of the flow is minimum, this is denoted by the suffix C, AC. So, up to this the flow is accelerating. Why? It is taking place with reduction in area. When flow takes place through an converging area, in case of subsonic flow also, supersonic flow it is just the opposite, you do not be confused with that. But so in our case always that when the area is converging, that the flow area, flow passage is converging by the contraction of the boundary, solid boundary, or by the stream surface, stream tube, then flow is accelerating because the velocity is decreasing and pressure is, velocity is increasing and pressure is decreasing, and this is the accelerating flow. In this direction the flow is, so therefore no separation takes place, because the fluid particle is being acted upon by the favorable pressure forces. So, pressure in the downstream is small, upstream is high. So, therefore, a fluid element suffers both favorable pressure forces and a push and higher kinetic energy. It is not a tug of war or race between the adverse pressure forces, adverse pressure, the pressure forces on a fluid element is opposite direction, whereas the kinetic energy is pushing it in the direction of flow, where the flow separation takes place. So, in accelerating flow there is no question of flow separation. So, therefore, it losses takes place because of the same separation when after the vena contracta the flow extends. That means, if I draw it in an extended view, that after the vena contracta is formed, when the fluid again expands to fill the passage, this part I draw it in a, that up to this vena contracta there is no loss, because fluid flows through converging section, that means accelerating flow. So, here only ADs takes place. So, therefore, it is usually told that the losses due to contraction, the loss of energy, mechanical energy is not due to contraction, but due to the expansion followed by the contraction. It is not due to contraction, but because of why expansion followed by the contraction? Expansion is needed. This is because the stream tube attains a minimum cross sectional area which is lower than the area of the tube. So, therefore, what happens? This is filled up like this. So, therefore, in this part, so therefore, it is basically the head loss or the energy losses, energy per unit weight, loss of energy per unit weight is due to expansion. That means, if I define Vc and V2, this is no way related to V1 now. So, this is simply Vc minus V2 whole square by 2G. And if again I write this in terms of V2 square, then I can write V2 square by 2G, then Vc by V2 is A2 by AC minus 1 whole square. Now, this A2 by AC has a terminology. Here the coefficient of contraction CC is defined as the area of the cross sectional area at the contraction zone, that is vena contracta, divided by the area of this pipe where it ultimately fills in. So, if this is there, this is 1 by CC minus 1 whole square. Now, this can be taken as K. So, therefore, it is expressed as H loss is, give another page, H loss is therefore due to contraction. So, therefore, due to contraction, the losses due to contraction is therefore, what is this? Losses due to contraction K into V2 square by 2G, where V2 is the velocity, that means this is the contraction, V2 is the velocity in this pipe. This K is equal to 1 by Cc minus 1 whole square. Now, here one thing, this area A1 and the V1 is not reflected here, but it is implicitly reflected through this K. This Cc is a function of A1 by A2, and if A1 is very greater than A2, then Cc approaches to the value of 0.5. What is A1 very greater than A2? That means there is a terrific contraction, which is physically the entry case. That means the fluid from a tank enters in a pipe, which is relatively smaller in cross section than the tank. This is known as physically entrance. So, entrance is simulated here when A1 is greater than, very greater than A2, and the dependence is such, we can find out Cc with the A1 by A2, that when A1 becomes very greater than A2, that means when it tends to a very high value A1 by A2, then Cc 0.5. So, therefore, these losses as a special case when A1 very greater than A2, and this we termed as the entry loss. That is entrance from a big tank to a pipe, similar to that of exit loss, exit from a small pipe to a big tank. Okay. So, now you get this concept, and now before I conclude, I will tell you about the pipes in series and parallel. Now, there may be different situations. So, pipes joined in series. Now, we consider pipes in series. Pipes in series. Now, you consider pipe like this. Now, it becomes extremely simple. One pipe, then there may be how to solve it. It is only another pipe, then again there may be a contraction, another pipe, and so on. It may go like that. We take 3 pipe in this case. The pipe is A, this pipe is A, this pipe is B, this pipe is C. Let the diameter of this pipe A is dA and its length is LA. This pipe diameter is Cc is not 0.5, I am sorry, K will be 0.5. The value of Cc is such, I am sorry, the K will be 0.5. My teaching assistant Dr. Poti has reminded me, I am sorry, here it will be K is equal to 0.5, so that 0.5. So, value of Cc will be such that 1 by Cc minus 1 whole square, K becomes 0.5. So, K as a whole is given as a function of A1 by, that means it is given through Cc. So, Cc will be such, K will be 0.5. Thank you, Sukumar. So, this is LB, actually time constant is there, and this diameter let us consider dB. This is LC. I want only that whether your concept is clear or not, because these algebraic steps anybody can derive. This is DC. Now, let us consider a pipeline like this, which consists of 3 pipes in series A, B and C of different diameters, and they are connected like that. B is bigger than A, then C is lower than B, maybe bigger or lower than A, like that. That means I create one expansion and I create one contraction in the line. And let us consider some energy at here 1, total energy head, and here head 2, and H1 is greater than H2. This is due to the total energy. it may be at higher height potential energy, there may be a high pressure. So, totally the energy, that is head here is higher and head here is lower. So, head causing flow is H1 minus H2 is delta H, and therefore, the flow takes place in this direction. How to write the equation? We know that H1 minus H2 is equal to delta H is all the losses. That is already proved. Obviously, the difference in energy is the energy loss suffered by the fluid inflow. What are the losses? Then let us first find out what are the losses. Now, your work is to find out what are the losses. First, here from H1 we neglect the entry loss, because here we do not know whether it is coming from a tank or not. We start from the entry position itself with this H1. Neglect it. If the problem is given that it is connected with a tank, then we will see that. So, first loss is that F L1 B1, that means the frictional losses. That means we take these frictional losses, that is here F, let friction factor in this pipe or friction coefficient is Fa La by dA, and let the volume flow rate is Q, which is constant throughout the pipe under steady case. So, let the velocity, average flow velocity in pipe FVA, flow velocity. They are varying, they may be changing because the cross sectional areas are changing. This is the frictional loss, plus we have to now identify the losses. There is a expansion loss, losses due to sudden enlargement, that is VA minus VB whole square by 2G. Then the skin friction loss in the pipe B, that is FB LB by DB VB square by 2G, plus what is this? This contraction losses, that means 1 by Cc minus 1 whole square due to this Vc square by 2G, plus what is this? The frictional losses, skin friction loss in this pipe, Fc Lc by Dc Vc square by 2G. So, all the losses are added. This is the total losses equal to the head causing the flow. Now, in the similar way as I proved, as I showed you earlier, we can write the flow rate, that Q satisfies this equation, pi ds square by 4 into Va is equal to pi dB square by 4 into Vb is equal to pi dc square by 4 into Vc. If you substitute all these Va, Vb, Vc in terms of Q, you get ultimately an expression that delta H is equal to head losses, which is equal to, if you substitute everything, then you get an equation like this, 8 divided by G pi square F A L A by dA for the skin friction of pipe 1, then 8 by G pi square 1 minus dA square by dB square, dA square by dB square. This is a simple algebra, you can do it. For the time that I cannot do it, dA 4 plus it is dA 5, sorry, dA to the power 5, then second term, then this 8 by all dA to the power 5, G pi square FB LB dB to the power 5. This is a long thing actually, this takes time, 8 by G pi square, and this is nothing, just a algebraic thing, 1 by Cc minus 1 whole square 1 by, it is what, dc to the power 4 plus 8 by G pi square Fc Lc by dc to the power 5 and Q square. So, these all are the resistances R1, R2. There are how many resistances? R3, R4, R5. That is resistance due to friction, skin friction in pipe 1. This is the resistance due to sudden enlargement. This is the skin friction in pipe B. This is the friction due to contraction. This is the friction in the pipe C. So, this can be represented as circuit diagram like this. All these series resistances, 5 resistances, as I have told, R1, R2, R3, R4, they are given by their respective value, and this is the Q square, and this is the delta H is H1. This is very simple, where R1, R2 are given by this. This way, if you can write the equations, you can solve. You have to find out what is the energy differences causing the flow, or head differences causing the flow. Difference is in head, that is energy per unit. This equals to the total resistance into Q square. Okay. Now, in case the pipes are parallel, there is another type of example where the pipes are in parallel, like this. The pipes are in parallel. That means these are the pipes, is a typical parallel flow. Then what will happen? If the pipe comes, the pipe A and pipe B. Let the length of the pipe A is LA, diameter is DA. Similarly, the parallel circuit problem LB and the diameter is DB, and the flow is coming here. Now, what is the difference? When the pipes were in series, the flow rate were different. Flow rate was same. Flow rate was same, but each pipe has a loss which is different. That means, if you consider the loss in energy in this pipe is different, this different, and sum of these 3 is the total loss, that is delta H. We can calculate the loss in energy only this pipe, then you have to take H1 minus the losses here. That means the typical series problem in electrical circuit also, the potential difference will be different, but this will flow the same flux. But here what will happen? The head at the junction will remain same. That means here if you consider H1, here it is H2, both the pipes will be under H1 minus H2, but the flow rate will be that if Q is the flow rate, QA and QB. Then H1 minus H2 for pipe A is FA, LA by DA into VA square by 2G, and H1 minus H2 is FB LB by DB into VB square by 2G. Now, this VA VB is related to this what? Because QA and QB, VA is 4 QA by pi dA square and VB is 4 QB by pi dB square. So, if you put in terms of QA and QB here, then what you get? You get what you get? You get that if you do it here, then you get an equation that FA LA dA, now VA is 16 QA square by pi square dA 4 by 2G must be equal to FB LB by DB. Again this is 16 QB square pi square dB to the power 4 into 2G into this. If this is defined as the entire thing as RA, and if this, as usual I did it, you define this as RB. Okay, that means 8 FLA, that you make it clear that this RA and RB, then we can write RA QA square is RB QB square, or QA is root over RB by RA into QB. Let this we define this at okay K, that means QA is KQB. And at the same time we know QA plus QB is Q. So here the task is to find out the division of flow. That means QA, if you solve this, QA is equal to KQB and QA plus QB is Q. If you know the entire total flow, this K by 1 plus K into Q is QA and QB is 1 by 1 plus K. That depending upon the resistance, the flow will be divided. You understand? If K is 1, then it is half. That means flow is divided equally. So K is what? You make this thing clear. Okay. Huh? Everything, yes, that is trivial. That is trivial. That everything is R. R into everything. That R. You take care of everything. This will be 8F L by D5 pi square G. This will be the thing. This you do it. This is very simple. School level thing. This is an algebra. This you make it clear. This is RA RB. So this is the thing. That means in a parallel flow, this is being done like this. Now I think this is the end, but before I stop, is there anything left? I will tell you one thing about the kinetic energy correction factors. Have you heard of it? Kinetic energy correction factor? I think they have not heard of it. Kinetic energy correction factor. Now so far we have told that when we represent the Bernoulli's equation, the kinetic energy we represent by V square by 2, but this V is defined as the average flow velocity. This is the concept which is based on the volumetric flow rate by cross sectional area. That means if you multiply with the cross sectional area with this average flow velocity, it gives the volume flow rate. So therefore square of this average flow velocity divided by 2 may not represent the kinetic energy. Then you have to define a average velocity based on the kinetic energy. So to circumvent this difficulty, what you do, when the velocity is expressed in terms of average flow velocity, we multiply a term known as kinetic energy correction factor. How it is done, I tell you. In a flow through a conduit, what is the expression of alpha? Let us consider the average velocity is defined, is written as V average. Then total kinetic energy is, then if we define the average velocity, we define the mass flow rate. This is okay, mass flow rate is this. And if we define the kinetic energy by squaring the average velocity, then we require a correction factor, as I have told. Kinetic energy per unit mass will be V square by 2 if this V is some sort of average velocity based on kinetic energy, but it is based on volume flow rate. So in that case an alpha is given. So therefore this is the total kinetic energy. This should actually be equated with the total kinetic energy of the flow. Okay. So sorry, there is no this such thing. This should be equated with total kinetic energy of the flow. What is total kinetic energy of the flow? Rho V dA times V square by 2. Clear? So therefore alpha becomes equal to what? Integration of rho V cube dA, because this must be equal to the kinetic energy. So kinetic energy is over the cross section integration. This is the mass flow rate, this is the kinetic energy, velocity square. This is the velocity at any particular location. This is not the average velocity, you understand. So therefore, if it becomes, if we consider this rho A V average cube. So if you consider this as, if you consider an incompressible flow, then this definition is V cube dA divided by A into V average cube. Or if you put the value of V average, what is V average? V average in terms of the distribution V dA divided by the area. So if you do that, the area cube, so that means area square will come there, V cube dA into V average cube, because V average cube is V dA, V average cube will V dA, time is up, so V dA whole. So you see, when we have a velocity variation over a cross section, we can use this equation or this equation to find out alpha. And in case of a laminar flow through a pipe, fully developed laminar flow, the value of alpha is 2. Value of alpha is 2. I will tell you again that value of alpha is 2. Okay, we can take some more time so that these things become clear to you. Alpha is equal to V cube dA by A into V average cube. This is the kinetic energy correction factor. A square V cube dA divided by V dA whole cube. Now, in a laminar flow, Hagen-Poiseuille flow, you know that V distribution is given as in the direction of flow R square by 4 mu minus dP dz. Dz is the direction of flow, 1 minus R square, where R is the radial coordinate, this is the radius of the. Or it can be written, this is twice of the average velocity. This already V average 1 minus R square by. Now, if you use this expression, you use it here, or it is already defined in terms of the average velocity, because this is twice of the average velocity. R square by 8 mu minus dP dz is average velocity. This has been done by Professor Suman Chakur. So, in terms of average velocity, it is better to put it here, so that you will get an expression that alpha is 2. In case of a turbulent flow, alpha varies between 1.01 to 1.15. So, therefore, it is approximately 1. In case of all turbulent flow applications, when we write the Bernoulli's equation or energy, mechanical energy equation, by writing V square by 2 as the representation of kinetic energy per unit mass, or V square by 2g as the kinetic energy per unit weight, where we replace V as the average flow velocity, does not make any difference, because the kinetic energy correction factor can be found for a fully developed turbulent flow profile to be some 1.01 to 1.1. It varies between that, and it is almost equal to 1. But in a laminar flow, there is a serious objection. You cannot express the kinetic energy as V square by 2, where V is the average velocity based on volumetric flow rate. This is defined as the average flow velocity in fluid flow. So, there you have to multiply with the kinetic energy correction factor, which is 2 in that case, and as defined here. Well, by this I conclude my talk. I have already taken more time, so there is no time to take the questions. So, if any questions on this pipe flow is there, at the end of my class today in fluid machines, in the afternoon, I may entertain some questions on pipe flow problems along with the part of fluid machines which I will be teaching in the afternoon. So, at the end of my fluid machines class, I may entertain, or I will entertain your queries on pipe flow, because the time is already, I have taken more time up for the tea break. Thank you.